So, hello everyone, I am Prashant Namekar. So, here I am representing Gaia Smart Cities. So, we are a small startup in a IoT space. So, what we are doing in Microsoft, we are trying to develop something, speech recognition on the small footprint devices. On the edge itself, we will try to debug everything, and on the edge itself, we will try to spot the keywords with a low footprint RAMs. So here is what we have proposed as an objective. So the main objective which we had is that we will be putting all the machine learning codes on the small footprint devices which is having a extremely low RAM size. And apart from this, we are using the audio input mics. So we have to take the inputs from the mic, we have to process that, we have to put that into the RAM. All the processing should happen in less than 100 milliseconds. So we will need a fast computing, means the model size should be less of the machine learnings. So other than that, we will reduce the number of computation requires to, also we will be focusing on the accuracy, what we can get and what we can achieve more. So this where we plan in, and what are the tangible outcomes we got in 1 month of time are, we have developed one generic tool. What that tool do is, you just have to pass the checkpoints file, like the TensorFlow model file to it. It will just create microcontroller independent libraries, that is .h files, that is C library files. You can directly port that onto the microcontroller thing. So other than that, we have developed our own machine learning libraries for the Cortex M4 and Cortex M7 for the LSTM and the fast GRNN, also for GRU thing. So in 1 month of time, we have almost 60 comparative experiments on different recurrent neural network models. Other than that, we have an Android app to gather the data set. So as currently we are using the Google 7 and Google 30 dataset for our models, we will be moving to some of the Indian languages. So we have worked on the different ML models are the DSCNN, GRU, LSTM, fast GRNN, and fast GRNN with low rank. So this is the microcontroller we will be using for our development purpose. The RAM size is, as I spoke, is 128 KB of RAM and 512 KB of flash. It is operating at a CPU speed of 180 megahertz, and same thing we have developed for M4 also and M7 also. We are using the main reason of using the M4 and M7 was it is having an inbuilt DSP instruction support, and some of the neural network libraries are supported. So for the DSP library, we are using for the dot product and the dot products, addition, subtraction, vector copy, and some of the FFT things. Also, we are storing the wave files in the .h format for the so offline training and all, and we will be saving the Hamming frames and all in the .h file itself. So I'll be passing the mic to Sneha.
Next, I will be taking you all to the workflow of keyword spotting. So basically, the data which we have is audio. So we cannot directly send the audio to the neural network to get the predictions. So first of all, we need to extract some features out of the audio, and here we are doing that. You can see there are speech signals there. We are processing them to get the speech features and then putting those features into the neural network. The neural network thus gives us the predictions of the audio. For this problem set, we have used the data set which was given by Google, that is called Google Speech Commands, and it has 30 keywords like yes, no. It has a background noise files also with it. We have trained the model for 30 class and 7 class problem. Also, the train, test and validation set split was given in the data set itself. So the features we have extracted are logarithm of the Mel scale filter banks. These are extracted for 1 second audio, so we get a feature matrix of dimension 99 cross 32. The data set is also normalized with the mean and standard deviation of the training data set. Next, these are the models that we are using. We are using basic RNN models. I'm sure you all are well aware of what is a RNN model, so I would not go that much into it. We're using LSTM and FastGRNN. These two are the different versions of RNN. So we have trained 3 different models: LSTM, FastGRNN, and FastGRNN with low rank. Now we have trained more than 60 models with different classes, optimizers, and hidden states, learning rates. Here are some of our results that you can see. We have the model, learning rate, optimizers, batch size, epochs, weight size, accuracy, and all these things. Then after doing all these experiments, we have finally reached onto one of the models which we decided to be deployed on the microcontroller. The model deployed had following specifications. It was a 7-class model with 16 hidden states, accuracy of 91.1%, and weight size of 3.6 kb. It was with background noise and quantized non-linearities. Next, I would like to call upon Shubham.
Hi, my name is Shubham, and so now we have trained our models in TensorFlow. So the important thing that we want to do is we want to get all these models onto our microcontroller. So the first thing that we need to do is we need to somehow convert the whole the TensorFlow models into a format that is recognized by C. So for that particular purpose, we decided to create a tool that will auto-generate these .h files for us. That will contain all the important information of the models, like the hidden weights, the input, the dense layer, the dense bias, and all and other information. Apart from that, we also populated our .h file with some constants which were very critical for audio processing, such as the filter banks, Hamming window, etc. So something that we would like to we observed during this during the course of the workshop was that the filter bank matrix was found to be sparse, and in the sparsity we observed a very unique pattern that actually allowed us to exploit it. So the pattern that we observed was something like this. So initially there were some zeros, then there were some non-zero elements, and then there were more zeros. So what is actually happening was we had a continuous length of non-zero elements, and which were preceded and succeeded by zeros. So now this kind of observation made us think, let's just see how many non-zero elements we have in this whole matrix. So the results that we found were quite surprising. So we used, as you can see, that the matrix, the entire matrix is 32 cross 257, which turns out to be around 8,224 total number of elements in the matrix. But in the whole matrix, we found that there were only 458 non-zero elements. Now that kind of got us to thinking, like if we are multiplying this matrix with another matrix of 257, then we have to kind of perform, for the whole matrix, we have to perform around 8,224 computations. Instead, why? That was majorly because we were doing a lot of zero multiplications. So instead of that, we said, why can't we represent this in another format and do only 458 multiplications corresponding to the non-zero elements? And part of it, after kind of thinking about how we could do this, we came up with this particular representation that we could just store the length of the non-zero elements of each row, the column index at which the non-zero elements start, and all the non-zero elements as a single array of 458 elements. So initially, as you can see, we were taking 8,224. We were storing 8,224 elements for the filter banks, but with this kind of representation, we just have around 500 elements, 500 floating point numbers. So an estimate of the size is like the first model had each floating point number is 4 bytes. It would have occupied 32 KB of flash, but with this kind of representation, we occupied only 2 KBs of flash, and secondly, the computations were much more faster. And indeed, this proved out to be very beneficial to us because we were using this multiplication every 10 milliseconds. So an estimate of how much time got decreased was initially our a model that we had done without using any kind of these, without using any of these optimizations, took around 1.58 seconds, an LSTM model. But when we shifted to a fast GRNN model, and we performed this optimization and several other optimizations, we brought down the time to 89 milliseconds. So there was a huge gain for us by using this kind of representation of matrix. So I would like to hand over the mic to Yash, and he'll explain the whole pipeline in some depth. Yeah, thank you.
Now here we have received the .h file. Now we need to do the predictions. In the microcontroller, we were having a DMA buffer of 20 milliseconds. It can store the audio sample of 20 milliseconds over there. Now here we have MEMS microphone from where we get the PCM values and we store it in our DMA buffer. Now in this DMA buffer, when it fills the first 10 milliseconds, it gives us a half transfer callback. And we keep that 10 millisecond audio in our 30 millisecond buffer, which is for feature extraction. We have made that 30 millisecond buffer because we need 25 millisecond of window so as to extract the features. And after that, when it passes that 10 millisecond, it keeps on updating this DMA buffer. Means while we transfer the data to our 30 millisecond buffer, it keeps on updating the 10 to 20 millisecond in this DMA buffer. And after completing this 10 to 20 millisecond, it gives a full transfer callback, and I pass that 10 to 20 millisecond over there. And similarly, for 20 to 30, after I fill that 30 millisecond buffer window over there, I use that 25 millisecond window to extract the features, and I get 32 log Melbank filter. And I initialize that fast GRN layer with 16 hidden units with zeros. And this is the first time frame of the RNN layer since we are using 0 to 25 millisecond. And this is the input vector, and this is the previous hidden states that we get. And we compute the next hidden units for next fast GRN gate. And I copy those weights over there. And we need a 10 millisecond stride over here. So I shift that 30 millisecond buffer, and the next 30 to 40 millisecond audio, we take it from the DMA buffer and again store it in our 30 millisecond buffer and again extract the MEL filter bank and again do the same for the second time frame of the RNN layer. And we do it for 99 steps since we have trained our model on 1 second audio which has 99 frames of 25 milliseconds with 10 seconds stride. Okay, here we are firing 20 fast GRN layers and computing the predictions over here. I will show you how it is working. Like if I give the 2-second audio over there, I initialize the first GRN layer at the start, and I compute that first GRN layer, and I get the prediction. Like 6, I got the prediction maximum of the probabilities of the softmax that we obtain after applying the dense layer. And I store it in a buffer. The buffer is called 10 previous predictions. Like it will store the previous 10 predictions in that buffer over there. And here I initialize the second fast GRN layer after 50 milliseconds. Like the first fast GRN layer is from 0 second to 1 second. The second fast GRN layer is from 50 millisecond to 1 second 50 milliseconds. And I again do the predictions over here, and I keep that data in my buffer which has 20 previous predictions, and I do the same again and again and again. And when I receive, since here we have like 5 times predicted 3 over here. So like it calculates the frequency, how many times a particular keyword has been predicted. If it goes more than 5 times, then it predicts that particular keyword, and it shows the output. And we do it for 20 fast, we apply 20 fast GRN layers over here. Like that 20th fast GRN layer is just starting just before 1 second and ending just before the second, sorry. And when the 1 second is completed, I again reinitialize the first fast GRN layer, and I again start it to compute for the prediction.
Hello, I'm Srinaja. So as we already discussed that we are converting the CKPT files to .h files so that they can be fed into the microcontroller and then used for the further processing. This is the tool that would help us to do it. First, all that you need to do is just upload the checkpoint files and the corresponding mean and the standard deviation files. So in the background, these files, they get uploaded into the Azure blob, and then the file starts executing, which converts those files into the .h file. And it gets again uploaded into another Azure blob. So once this process is done, you would be navigated to another page, which in this page, by clicking the download, you would be allowed to download the weights file that is generated and put in the Azure blob to your local system. And from this, you can feed it into the microcontroller. The best part is this whole tool, it can be used in any microcontroller. That is, it is independent of any microcontroller. That is because it uses the only basic integer data types. So you can use this tool for any other microcontroller. Right now it works only for the fast GRNN and LSTM, but again you can extend it to any other model. So in this 3 weeks, we had a chance, as Neha already mentioned, to work with around 60 models. We have trained the models using the LSTM, fast GRNN and fast GRNN low rank, and each of which we have trained with the 30 class and the 7 class. And again, each of those we have trained it with background noise and without background noise. So we've had some observations. Some of them are pretty evident, that is the 7 class accuracies are better than the 30 class, and the accuracies of without background noise models are better than the with background noise. So other one is the fast GRNN low rank model. For the higher number of hidden states, that is for 128 hidden states, it worked very well. It gave us the better accuracy. But when we were using it for the 16 hidden states, it kind of gave us a little less accuracy. So we had to narrow down between the fast GRNN and LSTM. And for the 30, and we were only keen on using the 16 hidden states with background noise model. So for the 30 class with background noise model, fast GRNN has given us the better accuracy. But when we were using the 7 class with background noise, the LSTM has slightly given us the better accuracies, around maybe 1% higher or less than 1% higher. But considering the model size, we had to choose the fast GRNN model. The fast GRNN model is 3 times smaller than that of the LSTM model. Because we have to fit this in a constrained device, we chose the fast GRNN model, and we've used the quantized non-linearities for it. So finally, we had a model size of around 3.6 kb with 91.1% accuracy. And apart from that, we had some other observations, like initially we used the tanh and the sigmoid functions, but while computing them on the microcontroller, it took a lot of time for the computations. But when we started using the quantized non-linearities, because they use only basic functions like minimum and maximum, the computation time kind of decreased. And while training the models, when we were using the quantized ones, the Adam optimizer worked well for us. And when we used the usual functions, the momentum optimizer worked well. Also, initially we started using the log functions, but because it takes the input as the double and we were providing it with the float, there was this type promotion that was happening, which took a lot of time for the computations. But when we switched to the log f function, it helped us with the computation time. And also, while training, we've noticed that after certain epochs, the loss kind of spiked up. So to overcome that, after a certain number of epochs, we've halved our learning rate. And we've validated the Microsoft's fast GRNN model in real time on our microcontroller, which has a single core processor. Yeah. I would like to give it to Bipin sir.
The motivation that we built was extremely small footprint, low computation, battery has to last for about 6 months, no connectivity, and what Alexa does, we wanted to do it completely on the edge. And those are the motivations. And then we realized that it could also solve these problems of security, of privacy, connectivity, and power. And that's what we have extended it to. In addition, the models that we have built, the framework that we have built is easily scalable across use cases. So while today we're doing it for six words, we're doing it for a certain number of one particular sector, we believe with the framework that we have, it can replicate easily. And also what we have seen, in fact, that's the microcontroller we're using is an ARM M4. It's a really small footprint. It's got 180 megahertz with 256 kb. In that, the power that it consumes is just 89 microamperes for every computation, per megahertz computation. And right now, with what we have developed, we just need 89 milliseconds for 1 second of speech analysis. So faster than you speak, I think we can analyze the whole, what you're trying to say. And this is done at a 3.6 kb, as the team mentioned earlier. Without quantization, if you do quantize, it comes to less than 1 point odd kb. So that's the STM32. This is the Azure IoT Sphere. That's the controller, which has about 500 megahertz. It's an ARM A7. It's superior, far superior in terms of computation power. We believe if we increase the number of word size, even to 100, and if we don't quantize, we can actually get a file size of a model size of not more than 9.5 kb. And this actually exceeds the number of use cases that we can apply it to. We're trying to extend it to services in retail, hospitality, services, and industrial manufacturing as well. Pretty much, which doesn't require connectivity or power. These are the number of use cases that we believe we can. I'll move fast. Even panic detection in cabs, feedback, usage in cities. All of that is where we can. This is what I want to talk about. So yesterday, I met the gentleman from Intel, and they have a smart home application which. They don't want it to be. They want it to be lightly connected to the internet. They want a lot of processing on the edge itself. They don't want for every analysis like Alexa does. They don't want to contact the server, and they believe this can be a good use case. Similarly, in the connected car, just for starting a car, they want to move away with the start button, and if we can give them the ability to start just by talking, and the analysis and the fingerprint, the voice print can be analyzed on the edge, I think it solves a lot of problems for a lot of people. Connectivity, security. What we're trying to do is increase the number of languages. In fact, we built this model to actually replicate across languages. We have to work on false positives. We have a significant number of false positives right now. We want to extend it to more use cases. We want to design use cases. In fact, you will see the demo that we have. It's a pretty small footprint thing with power. It can go over, I think on a single AA battery, we think it can last for about 2 months with at least 1,000 usage per day. We want to do beta trials. We also want to do adding a speaker to it. And we have one model now. We're just doing speech recognition. We would like to do gender detection, sentiment analysis also on that. And we believe with quantization, the footprint shouldn't exceed so much. I'll end with this. And without ending, I can't do it without thanking the Microsoft team, Aditya, Harsha, Prateek, Bridge yesterday who helped us solve the real-time voice problem. We were doing everything off the drive, but we did real-time just last night. We had help from Bridge. Satish, Chris, all of them, thank you so much. And without further ado, I'll call Prashant to give you a demo.
Okay, so meanwhile, I can give a demo on the small kit. So this is a STM32M4 microcontroller. So it is having a RAM size of 128 KB. So we are having the biggest challenge that to take the audio real time, to process that prediction, everything we have to do in the small amount of time. So I'll be giving the demo on that. So you can see that for prediction, we are just for prototyping, we are using the LEDs to display. So here, if I say yes, this LED should blink. This LED will be continuously blinking just to show that it is on. And if I say no, it should blink down, and similarly for others. So one thing we have just, yesterday night we have cracked this. Actually, yesterday night it became, so, okay, I'll give the demo. That's the small power source. Okay, you can see that the red LED is blinking here. This is the power. Yes.
One.
Okay, it's blinked one toggle.
One. One.
You can say other.
4.
Okay, 4 it's triggered the top one. Okay, cool.
But the S is still on.
Yeah, there is
Yeah.
some false trigger.
It is
We
just
will figure
toggling,
out that.
but
Just we are having this pretty much confident that we can crack this more. Just 1 month we have achieved this thing.
So with that extension of the model, even quantization, you can even detect sentiment. We can even do sentiment analysis and panic, but panic can be detected easily without even contacting the edge. So those are the USPs of what we're trying to do.
So actually, we have used the YouTube burst noises and all. So we are cracking that also.
So it does noise cancellation, and all the background noise is taken away too.
We'll do a lot of experiment. Yeah, it has some features in that. So that signal to noise ratio of around something. It has. We haven't studied that. We were more focused on the model things, achieving that to fit in that. So now we'll focus on the other parts also.
But the size is what is really
Yeah.
exciting for us.
Challenge
The size
was
and the
to
power
achieve
consumption.
this in real time.
Yeah, all of this in less than 89 milliseconds is what we calculated.
What helped us to achieve this was one thing was the sparsity matrix, what the mail bank filter and all he talked about previously. It was taking some around 8,000 computations. So after that, we observed that we don't actually need that much computations. We have reduced to around 450 or something. And other than that, some DSP instruction sets and all. That's it.
So
Okay,
this is
you
also
can
done.
show the generated
Take a
one.
couple of minutes.
Oh.
But these are already.
Yeah, you can show them. You want to connect it to the monitor? No need, we can show you.
Yeah, you can if you.
Okay, connect to monitor. I'll show this.
Question in the meanwhile, are you going to deploy anything in the next month when you get back to work?
If you get the grant, yes.
But seriously, in terms of your deployment out, which is the next step?
I think there is a couple of things we need to crack before that. One is the false positives. We need to reduce false positives. We'd like to increase the languages, because in India, the language is.
Which domain specifically, if I may ask, where is it going to go? Where is your next use case?
The first use case, it would be either in the Airports Authority of India. We've got 32 airports signed up for this. Or it would be in the Swachh Bharat mission where it's toilets. And the thing with toilets is people don't want to come out and press a button. Because they think it's dirty, so they rather say something than press a button. And that's why speech came in. I mean, voice came in. I mean, voice. In fact, they want to do sentiment analysis too. And we have done sentiment analysis. We have done sentiment analysis, but not, I mean, the footprint is too small to do today, and we couldn't crack it. But these are requirements that come in from the market. It's not, we haven't invented them.
So, I have a question. I mean, since you talked about like feedback systems as the target application, right? I would imagine that you would be worried about like adversarial inputs. In the sense
Example?
that if I'm using it for voting or I'm saying, oh, I want, and in fact, people have shown attacks against these sort of voice activated systems. You can do like ultrasonic attacks that you can't even figure out what they're saying. And you can actually do ultrasonic attacks from a distance, very, very low sort of SLR that actually kills the machine learning. So, have you guys thought about like?
No, honestly, no.
If you thought about a feedback system and I want to like sort of totally sort of new
What-
controllers deploying them, I would just have an ultrasonic transmitter and keep like sending no votes or whatever, whoever I want to vote for.
No, so we haven't thought about that. But what we have thought about is of one person giving multiple feedbacks. And there, on the Qualcomm, I mean, on the Snapdragon, which has got a higher processing, so we've analyzed the speech print and tried to detect duplicates there. We haven't done it on this because of the size, but I was assuming we can work out how to detect duplicates in the voice print. We don't need to know who it is, but just the voice print analysis can help us remove. No, but this.
Actually, I think more interesting, sir. This is might be a research question, right? I think one of the things that people in the adversarial machine learning community have found is the reason these machine learning models can be fooled is because they're kind of like they're overfitting a lot. So I wonder, because you're building a compact model to fit on these devices, whether they actually might be, as a side effect, might be more robust to adversarial inputs.
We'll have to. We hope IoT sphere has some kind of security checks on that.
Actually, Manik and Pratik, I don't know. I'm quite curious actually.
Yeah, actually, I suspect, I mean, because the people have said like the reason adversarial machine learning works is because, hey, these things are overfitting, and if you're building a compact model, it's naturally sort of robust. I would.
Have you studied this?
See, we can't shove it moving at first to study this, right? So we don't need an analysis. Our model is built itself now, as you see. So it needs a lot more effort to get to a stage where it doesn't fire and background noise. So it's
Hi, this is Manik. So we haven't studied adversarial attacks. I doubt we would be able to cope with adversarial attacks, but I think we get some robustness to sensor noise. So if your sensor is not very good quality and because of the quantization, etc., we might be robust to that. But I doubt we would be able to overcome sustained adversarial attack?
So if we move the problem away and handle it differently, so the system works by proximity. If the whole system can work because of proximity, you can put a proximity sense and then make it active only when you're close to it. You could probably do away with that unless somebody comes close with the, So there are possibly other ways to offset that thing, saying that don't switch it on. In fact, that helps us save power too. Don't make the system active without somebody coming close, because you're interested in feedback, and a simple proximity sensor can help us solve that.
I also have a question, if you don't mind.
Sure.
So if you have hundreds of kilobytes of RAM and flash available, do you really care whether the model is 1 kilobytes or 20 kilobytes? Can you say a little bit about like how much space are you going to allocate for this RNN or LSTM amongst all the other things you need to also fit onto the microcontroller? So that was one thing.
We'll try
and
to
the second
increase
thing was
the...
I missed a bit of your presentation, so perhaps you already spoke about this. So maybe more than RAM, your battery consumption might be more of an issue. So did you test whether an LSTM versus a fast GRNN, how much was the consumption, how much was the computational cost and the battery requirement, that battery that you were saving?
So we calculated hypothetically, we just didn't do experimentally. We didn't have the opportunity to do experimentally, that's one. Number two, the size does matter if you're actually looking at trying to increase the feature set or other functionality. I mean, as we spoke some time back, if you try to do sentiment analysis, or if you try to do gender detection, or if you try to do age detection of the person who's talking, well, these are all things that can come in. And if you can extend it to include all these, I guess size does matter.
But let's not speak hypothetically. For your concrete application, how much space do you have reserved, or how much space have you got allocated or earmarked for the RNN or LSTM?
This microcontroller has 128 KB RAM, and for this entire application, it consumes 123 KB of entire RAM for complete computation, prediction, and taking in the input data. Actually, most of the memory is going for that 10 millisecond
So the
callback.
RNN will fit on the flash, right? You won't have the RNN and RAM, I assume.
No. But we need to have some matrix over here in the RAM so as to take the weights from the flash so as to compute it in the RAM over here.
Sorry, I didn't follow, but maybe I'll take this offline with you.
Sure.
Okay.
Also,
okay. So you're hypothesizing, like, following from Manik's point, whether gender and sentiment analysis can be done with RNN is not clear. I don't know if you've tested it.
No, we don't know. We don't know.
One of the previous Krupa was using RNNs to do audio reception, and realized it's not clear that it's a good fit. So maybe you should try it before.
Yeah.
I think we're running out of time, so thank you again.
okay, thank you.